Okay, so again, equations of uniformly accelerated motion. You got to know what to do given non-uniform acceleration. You got to know how to get these equations and use them. Set up a uniform acceleration problem. Declare your x naught. Identify 3 of the 5 quantities. If you got 2 objects, you got to identify 3 of the 5 quantities for both of them. You could declare x naught 1, the initial position for one of the objects, and then from that you can figure out what x naught 2 for the second object is. Write the equations and solve simultaneously, which often involves setting 2 equations, two expressions equal to one another, but not always. Sometimes you got to get a little trickier. Motion in 2 dimensions. Yeah, he said you're going to have to do that. That's why I turned the camera on. So be sure to get all the stuff I do here, okay? So good luck, and take care. See you next time.
I'll see y'all Wednesday.
Good. Okay. Motion in 2 dimensions. Okay. Each dimension's independent of the other. I'm talking about like the x and the y directions. You set up your coordinate system. As convenient. You can have it level, you can have it rotated. Okay? If you're dealing with projectiles, for example, you'd better have it level, because then you have 0 acceleration in one direction and gravitational acceleration in another. You have a level coordinate system. A equals 0 in one of your dimensions. A equals acceleration of gravity downward. In the other. You set up your equations. I'm going to write it over here. A little hard to read. You set up 2 equations and solve them simultaneously. That's your strategy for projectiles. Sometimes those equations are tricky to solve. Okay, if you have the situation where the ball goes off the ramp at an angle, you get some pretty tricky equations there where you got to maybe, well, you get some tricky equations. Even trickier is where you know the initial velocity and the horizontal range, let's say, and you got to find the initial angle, and you got to solve for the angle, and that gets quite tricky. So you got to watch that. You got to do what's necessary on those equations. Now, of course, on a test, if you at least get them set up correctly and can't solve them, you're going to get some partial credit. and get them set up is probably half credit. Solving them right is the other half. Solving them right and interpreting your solution. Set them up and interpret what your solution would tell you if you could find it. Probably worth just a little more than half credit. Okay. Okay, that's motion in 2 dimensions, and then also that's one of the paradigm cases where you have motion in 2 dimensions. The other is circular motion. All right, that is A cent equals v squared over r, centripetal acceleration equals v squared over r, and that's really your key on circular motion. Now you get into vertical circles and stuff, which we've been over. That's going to give you your net force, okay? Multiply that by your mass. You have your net force, and you got to combine that with any other forces that might be there, like gravity and so forth. Okay? You got to know that. Okay? For forces, first of all, you know net force equals mass times acceleration. Equilibrium, acceleration equals 0. So net force is 0. So the sum of your forces in the x direction plus the sum of your forces in the y direction has to be 0. And that's what you apply to solve problems. And you, of course, need to use free body diagrams to identify your x and y components of forces. I'm going to add one more thing. So the sum of all forces, F net is 0, so the sum of all forces is 0. And this is the sum of force vectors. And every force vector has an x and a y component. Sometimes one or the other of those components might be 0, but you still have an x and a y component. So if the sum of vectors is 0, then the sum of their x components has to be 0, and the sum of their y components has to be 0. And you want to understand that's an important point that relates everything conceptually to your net force being 0. Okay, so there are many cases. You have things on inclines, you have masses on pulleys, Atwood machines. Of course, that's into dynamics. You have suspended masses. Suspend from a rope at an angle here and another rope here, and then the mass is suspended vertically. Wide variety of cases, and your text and your Mastering Physics does a really good job of running you through a variety of cases. But those are your principles. Everything comes down to these principles, and you want to see in those examples how the principles play out so that you're able to solve problems even if they're unfamiliar. Okay. Now I'm going to leave some stuff out here. But we'll say more next time. And you have two chapters basically that work out what happens with forces, okay? That would be chapters 4 and 5. And they apply Newton's second laws. And I guess I ought to mention Newton's second laws. Newton's laws, you have the first law, moving in a straight line. If you're moving and there are no forces, then you have no acceleration, and you keep moving in a straight line forever without any change in velocity. I'm not going to write all that out. Your third law is action-reaction. To every force, there's an equal and opposite. Any force acting on an object, you have an equal and opposite reaction of the same type of force. Okay, you have action-reaction pairs, and those concepts again, your mastering does a really good job of helping you identify action-reaction pairs. Okay. Okay. So, talk about energy. And if you want a little compound interest here, you've got it. Get it fast because it's going away. Put that over here. That one has been done and needs to be washed. I just didn't get around to it. Okay. I'm going to say a little more about work energy because that's what we're into right now. Yep, you're right. It's either writing with invisible chalk or had the camera wrong. I guess there are other alternatives in my perception. But if you're seeing what I'm seeing, I tend to believe I don't have the camera right. Okay, so kinetic energy of mass m at velocity v. I'm going to use this definition. Your book uses a slightly different definition that's totally equivalent to this one, though. Is the work required for the net force to accelerate the mass m to velocity v. Now, it can be proven with a little calculus. It doesn't matter if you have a constant or variable force, the work done is always the same. Okay, so one way to illustrate that with a graph is in general, the work done by force F through displacement x is the area under the graph. Okay. Also, this is equal by basic calculus to average force times displacement. And average force times displacement is a good way to estimate the work done. For example, if you have a magnet, that's a pair of magnets accelerating a toy car. And let me just digress kind of quickly. I don't think anybody submitted that latest thing I asked you to do with the magnets in the toy car. It's 30 minutes probably to get your data, 30 minutes to report it. It's short, and you really need to do it to get a grasp on the energy. And it was assigned, I think I put it in an assignment dated like Friday. So check your assignments page and get that done, okay? It's fairly short, and there's a lot of insight, a tremendous amount of insight to be gained by analyzing that. We talked about it last time actually, but we want to actually be sure that we get a good analysis of that experiment before the midterm. Okay, well anyhow, okay, the idea of average force times displacement. Okay, I'm going to draw 3 straight lines indicating 3 candidates for the average force. Oh, got too much stuff around here. That board I just set down there almost tripped me, but fortunately it's impossible to fall in this room. It's impossible. There's no way anybody could fall in this room. If you totally lose balance, your whole body is not going to change its angle of elevation by more than 10 degrees. Okay, now, so, okay, you got a line here. That's a blue line. Here's a purple line. And here's a green line. Which line do you think best indicates the average force? If I'd have known I was going to do 3 lines, I'd have drawn a slightly different picture so the lines would separate a little more. Well, one way to look at the average force is over the period or over the displacement. The displacement is from here to here. Over the displacement, the average force should be the one, let's see how I did here, that if you look at the area above the line for the average force and the area below the line for the average force, let me just use green to shade that. Okay, the shaded region above should have the same area as the shaded region below. Okay, well, in this case, which one is greater, the shaded area above or the shaded area below? It's pretty obvious that there's more shaded area above than there is below. Okay? So here I'm going to say well, then I'm going to say the average force needs to be a little bit higher. You need a little more area below, so you got to raise the thing up, but not too far or you get too much area below. Okay? So of these three, I'd say the one in the middle of purple is probably best. Okay, well, that's important. Now let's come back to definition of kinetic energy. If your net force is constant on a mass m, that acceleration is F net over m. So if we're given a delta x, remember that's what I used to stand for x minus x naught. Vf squared equals V naught squared plus 2a delta x. If V naught is 0, because we're talking about the work required to accelerate from mass m to velocity v, I didn't say from rest. That's important. I knew it, I just didn't write it down. Okay, then your V naught is 0, so Vf squared is 2a times delta x. So Vf squared is 2F net over m delta x. So F net delta x is 1/2 m Vf squared. That's your final kinetic energy if you're starting from 0. So that kinetic energy can be defined as 1/2 m v squared. Okay? Very simple. Your book does it using the same equation, but it has a non-zero V naught. Well, V naught's non-zero, then you get F net delta x equals 1/2 m Vf squared minus 1/2 m V naught squared. Final kinetic energy minus initial kinetic energy. So you need to understand that. That's the beginning of understanding of energy. Now we'll go on with this next time because we're out of time. So I'm going to turn the camera off.